Okay, in this video we want to broach the topic of permutations. So this is all about if you've got like a number of elements, say n elements, um, how many different orderings of size r can you form from that? So I mean this seems kind of abstract. So one way that I like to think about it is if you take and it actually comes up like if you've ever played a musical instrument, you can put your hand down on it. Let's say you just put your hand down on a keyboard and you could say like C D E F. You've got like four notes sitting there, or however many notes you want to take. And so a question might arise, like what are the possible melodies, in this case without repeating notes? Like theoretically, what, how many possible melodies can you form from a given number of notes? Um, and what are they? So like what's the size of this set and what is the contents? Okay, so we're gonna just like to try to start building the intuition. We've got the simplified piano, say, or guitar that only has four notes. And I've just labeled them C, D, E, and F. If you've ever played the piano, it'll be sort of obvious why I did that. Um, okay, so what we can start doing is just writing out the different sized permutations from these four notes and see if we can notice a pattern. Okay, so this is sort of the trivial base case here of like, let's say your melody is only going to be one note long. Well, how many different ways can you do this from your four notes? Okay, well you're only going to play one note, so you're limited in choice of melodies to the number of notes that there are. You could either play the C, or the D, or the E, or the F, and then you're done. So you've got these very short, not really melodies per se, but well, they're melodies in that they're single pitches. And actually, let me just interject that in the next video, I'm going to be contrasting these permutations, which are like melodies, to combinations, which are like chords. The difference being that in the permutations, the order of the notes matters, and it defines the permutation. So if I played C D E, that's like a distinct permutation from C E D. Whereas if I played the C, the D, and the E all together to form like a chord, that would be a pretty crunchy sounding chord with all of those major seconds together. But nonetheless, like that's the basic idea, is that in combinations the order doesn't matter. You're looking at sets of groupings, whereas in permutations it's all about the order. It's like that's the essential thing. Okay, so let's move on to our two note permutations. You could imagine on the piano you could play C D, or you could play C E, or you could have played C F. But outside of that, you've exhausted the possibilities of two-note melodies that you can play starting from C. So suppose you had started on the D. You could play D back down to C, you could play D up to E, D up to F, and then you're sort of at a loss for different things you can play from D. But in any case, from each starting note, you then have like three different things that you could play. And so we're just totaling these up, and we see that there's 12 total permutations, four total notes to choose from, four elements, length 2, r equals 2 permutations, so we get npr 4 p2 equals 12. Okay, and then we go on to our three-note permutations, and we do a similar sort of thing. We list out our permutations. We go C, D, E, C, D, F, we go C, E, D, C, E, F, and we list out our permutations here, and we see that there are 24 of them. Okay, I'm just gonna add this in here because like really, the way you could look at it is in terms of like how many choices you have. So suppose you know you wanted to play like a 4-note melody. Well, for the first chance, you can play any of the notes. So there's 4 possible ways to strike the first note. And once you've done that, you've eliminated one of the notes, and you're limited to 3 for the second. And so, this is really your answer for a 2-note melody. If you add in a third note, you now have 2 to choose from. But we can see that, once you've narrowed it down to only having 1 note remaining, like, you don't really get more permutations there, because like the choice, like you've sort of already made your bed. Now you have to lie in it. There's only 1 additional note to choose from. Okay, so anyway, and in terms of like if you're into set theory and you're into like forming power sets, this like 2 to the n thing for the power sets, it's kind of similar to this. Anyhow, maybe I shouldn't have said that. I'm glad I said this. Forget about the thing about power sets. Go watch a video on by someone who actually like can do abstract mathematics. Litsky would be a good guy to check out for that. Okay, so what was my point here? So like we've got these totals, and the whole thing we want to do is like just extract like a pattern here. If you have any sense of working with permutations, you know that this factorial thing is going to come into it. So 4 factorial being 4 times 3 times 2 times 1. Like we want to use that. But let's just see how this works out. Here we've got 4 times, well, we can call it 1. Here, our 12 could be 4 times 3, and then times something that's equal to 1. Here we've got 4 times 3 times 2 times something that's equal to 1. So it's like, so we have something to do with 4 factorial. And it's like we start computing it, but at some point we stop. We have to like sort of stop the bleeding, so to speak. And where we stop the bleeding is a function of the number of elements R that we're selecting. Okay, the number of elements out of the total elements that we're selecting for whatever our permutations of interest are. So, in this case, if we were to carry on the factorial notation, like we could instead of just saying multiplying by 1, that would be the same as 2 factorial over 2 factorial. And that's nice because it gives us this property that we could keep 4 factorial in its full form in the numerator. And then we're just dividing out something factorial in the denominator. Okay, that's beautiful, and that works in each of these cases. So what is that something? Well, you can see that if you take the total number of elements from which we're drawing, and we subtract the number of things in our permutation of interest, it's that factorial. So in this case, 4 minus 1 is 3 factorial. We divide out the 3 factorial. Over here, 4 minus 2 is 2 factorial. Over here, 4 minus 3 is 1 factorial. And in fact, this is the formula that we were hoping to see. It's always going to be n minus r factorial in the denominator. And so our general formula for permutations from a set of n elements, permutations of length r, is going to be n factorial over n minus r factorial. And I encourage you to investigate this for yourself. Hopefully this has been of some help to someone. Thanks a lot.